there are some related questions that can be asked in theory examinations and also in biology examinations. So what are these? What is cardiac axis or what is electrical axis of the heart? Or what do you mean by mean cardiac vector, mean QRS axis, or are synonymous? Okay. Then what is the normal electrical axis and abnormal axis? RAD stands for right axis deviation, LAD stands for left axis deviation. Causes of LAD and RAD. And what is Einthoven's triangle? Important questions. What are Einthoven's law? Again, how electrical axis or cardiac axis or QRS axis is determined. There are various methods. One is easy method. By seeing the electrocardiogram, immediately you can tell that whether there is axis is normal or there is right axis deviation or left axis deviation. There are some other methods using, it is using Einthoven's triangle method. So that method we also learned. Another method is there, which is hexaaxial system. So hexaaxial system also just you can just roughly calculate or assess the electrical axis. Among the three, this right side reference system using Einthoven's triangle is accurate one. Okay. So before I start elaborating the cardiac axis of the heart, I want to again explain in very short way what we mean by ECG. ECG is electrocardiography. In short, electrocardiography by which we record the electrical activity of the heart. Okay, so it is the method. And electrocardiograph is the machine. I asked in biology examination, but most of the students couldn't answer properly. Electrocardiograph is the machine by which we take the record. Okay, and electrocardiogram is the recording. The straight we obtain, the different wave patterns we get. This is the electrocardiogram, not the graph. Okay, be sure about this. Now this electrical activity of the heart, how it is generated in the heart and how it is spread to the body surface area. So let us, heart can be, you can think heart as a battery. Okay, so battery is having two poles. One is negative pole and another is positive pole. So because of this polarity, two polarity, dipole, so there is flow of current. And since the heart is immersed in a volume conductor, means the volume conductor is, there is a lot of tissues and body fluids which are conductive, good conductor of electricity. So heart remains within a volume conductor. So the current generated in the volume conductor, it is transmitted throughout the body. So suppose this part of the heart is depolarized, means outside is negatively charged and other part yet to be depolarized, positively charged. Suppose this is the atria and this is the ventricle. So because of this is now a dipole. So because of this, there will be flow of current. There will be flow of current, and this current, since this heart is immersed in the volume conductor, means electrolytes, body tissues, through this, the current can be spreaded over the tissues. Now this electrical activity, now this part may be spread throughout the whole heart. This is a depolarized, the whole heart may be depolarized. Now there will not be any current. Now there will not be any current. And when heart is totally outside circuit is positively charged throughout the heart, then again there will not be any flow of current. So voltage will be zero. If you see in the galvanometer, you will get a straight line. That is called isoelectric line. Okay. So because of this, since this current, initially a small part will be depolarized from SA node. The SA node will depolarize the nearby. Suppose this is the SA node and these are the cells, nearby cells. Now they will be negatively charged after depolarization, and they will again depolarize their nearby cells because these are attached by syncytium, attached by this gap junctions. So electrical impulse will be transmitted. Nearby cells will be transmitted. In this way, these are yet to be depolarized. So we can see some portion is negatively charged, some portion is positively charged. As a result, what happens? A dipole is formed. A dipole, this is a dipole, this is a dipole. Positive, negative, this is a dipole. So when there is a dipole, there will be flow of current. So there will be flow of current. Okay, now we can see lot of small dipoles are generated in the atria, and it can also be generated in the same fashion in the ventricle. So because of this, what is this? Voltage is not always fixed. It is changing. Every moment it is changing. The area of depolarization is increasing. Areas of polarized area is decreasing. So as a result, what is happening? Flow of current and the amount of current, this is the voltage difference is also changing. This change in voltage, this change in flow of current also spreads throughout the body surface area. Now that we record, if we record this electrical change, since these are transmitted to the body surface area, body surface, so we can record these changes. What changes that are taking place in the heart, that can be recorded from the body surface area. And this recording is actually done by electrocardiography using the electrocardiograph, and with this machine we get the electrocardiogram. And since this wave is changing, every moment it is changing, that's why the waves that we get, that we record, are also of various, it is also changing, it is not fixed. Sometimes it is giving a positive wave, sometimes it is giving a negative wave. So in this way, different waves we get. Now, this electric activity, how we record? We record this using lead system. Okay, we have 3 types of lead system, 2 types particularly. One is unipolar lead, one is standard limb lead. One type is standard lead, another type is unipolar lead. Standard limb lead are 3 types: lead 1, lead 2, and lead 3. How we get lead 1, lead 2, lead 3? We record using electrodes. These electrodes are connected to the ECG machine. There are 2 electrodes. One is positive electrode, another is negative electrode. The positive electrode, in case of lead 1, suppose this is right arm and this is left arm and this is left leg. Okay? So, connection between these two, left arm and right arm, forms lead 1. Lead 1. And here, this is lead 1, here it is having the positive pole and right arm is having the negative pole. And how lead 2 is formed? Lead 2 is it records the potential difference between right arm and left leg. Okay, so this is lead 2, this is lead 2, and positive terminal remains in the leg and negative terminals remains in right arm. Okay, then lead 3, it is the difference, potential difference that we record in this electrocardiogram machine between left arm and left leg. Here, the negative terminal remains in left arm and positive terminal remains in left leg. So, this is lead 3. You have to remember this thing. This is lead 1, positive wave, positive terminal and negative terminal. And lead 2, this and leg. Positive terminal there, negative terminal here. So this is always negative. And lead 3, connection between this. Here, positive terminal, negative terminal. That means left leg is always positive. Okay. So this is standard limb leads. Okay. And there is unipolar limb leads. What is unipolar limb leads? In unipolar limb leads, we have one electrode which is positively charged, positive electrode, and this is exploring. It explores different portions of the body. Another electrode is indifferent electrode. Okay. So unipolar limb leads are again two types. Two types. One is augmented limb leads. Another is precordial leads or chest leads. What is this augmented limb leads? The augmented limb leads, here two terminals, for each two terminal is there, one negative and positive. Positive terminal is there but negative. While I will be recording what is the voltage difference of left arm and the other electrode, all other electrodes are joined and made potential 0. So against 0, what is the potential difference with left arm? That is AVL. Okay? And now AVR, positive electrode in the right hand, and all other electrodes connected together and made it 0. So I am recording the potential difference in my right hand in respect to 0. Okay? So this is AVR. Similarly, we can record ABL. So this way we record ABR, ABL, ABL. So these are three types: ABR, ABL and ABF. Okay? F means foot, L means left hand, R means right hand. Okay. So always these are positive pole. These pole are always positive. And the other pole gives 0 voltage. Okay, we are comparing against 0. Another set of precordial leads are there. Here also one exploring electrode is there, another is indifferent electrode. Thus exploring electrode explores my chest from different locations. There is position, I will not explain it here now, B1, B2, B3, B4, B5 and B6. These are covering the anterior surface of the heart, inferior surface of the heart, lateral surface of the heart, posterior surface of the heart. And also means it sees the heart, these leads, chest leads, it sees the heart from different locations. And these are important in localizing the pathology. Suppose infarction. There is infarction in a particular area of the heart muscle. Where is it? Whether it is in anterior wall, or in the septal wall, or in the inferior wall, or in the lateral wall, or in the posterior wall. So this can be localized using these leads. That's why we record electrocardiogram from 12 different ECG leads. 12 different leads. These are lead 1, lead 2, lead 3, ABR, ABL, ABF, B1, B2, B3, B4, B5, C6. In some, when it is needed to get accurately diagnose the posterior wall infarction, in that case we record B7, B8, B9. So normally we don't do this, but we can assess seeing the changes in B1 and B2. Okay, so this B1, B2 not only gives idea about the septal wall, it also gives idea about the posterior wall. Okay, so this will be discussed in detail when I will be elaborating myocardial infarction ischemia in my next class. So you try to remember in ABR, this is ABR, it is positive electrode. And ABL, here is the positive electrode, ABL, it is the positive electrode is here, okay? And in case of bleed 1, positive electrode here, negative electrode here. In case of bleed 2, here it is negative and positive electrode at the leg. And in case of bleed 3, positive electrode at the leg and negative electrode at the hand, okay, left arm. So this arrangement you must know, okay? Now, another thing, the electrical activity that is generated in the heart, it is every time it is changing. That's why we get different waves. Okay, as a node, it produces a cardiac impulse. Now it travels. This impulse is travels to the AV node. From the AV node, it travels into the ventricle. Okay, throughout this traveling path, what is happening? The area is depolarizing. In this way, one activation front. What is activation front? Suppose this is one of the cell next to SA node. The SA node depolarized them. So outside was initially positive. Now they became negative. Now it is depolarized. Okay. And neighboring cells is positive, yet to be depolarized. Now we can see negative, positive means one battery, small battery. Okay, so these are dipole, small dipoles. When there is dipole, there will be flow of current. Now since because of this, they will be depolarizing this. Okay. Now we can draw a line. Hypothetically, we can draw a line. At one side, it is negatively charged. At other side, that is positive. That is yet to be depolarized. These are polarized. These cells are polarized, and these cells are depolarized. Now, in the next very moment, what will happen? They will depolarize it. This will depolarize it. Now this activation front, this activation will come here. So it will move here. Again, these cells which are positive, they will become negative. There will be a new area where current will be flowed from here to here. Again, this activation front will be proceeding further. In this way, these dipoles, numerous dipoles are formed, and this activation front is proceeding to covering the whole atrium. When whole atrium is covered, then the whole atrium is depolarized, but the ventricle is yet to be depolarized. Now what will happen? we know there is some junctional tissues. The atrial impulse, this cardiac impulse, this voltage flow of current will enter into the ventricle through AB junctions. But while traveling through the AB junction, there will be delay. There will be delay. Okay. After this delay, again they will travel along the bundle of fish. Again, then into the Purkinje fiber, then into the which layer? Which is the innermost layer of the heart? Endocardium. So first endocardium, then endocardium to outward. Endocardium to epicardium. So in this way, it will flow. The current will flow. During this flow, current is every time changing. This current is flowing and this activation front is also changing. Because of activation front changing, there will be different area of the heart is at different time. It is some, say at a particular moment, a particular area is deployed, but in the next moment, the area is increased. Okay, in the next moment, area is decreased. As it is, the potential is gradually changing. It is not fixed. And because of that, we get different waves. Sometimes it is P wave. And these vectors, I told about the dipole. Dipole actually they generate vector. The one term I uttered, this is vector. Those who have studied, they know what is vector. Vector is a quantity. What is vector? Vector is a quantity. And what quantity is having? It is having two other things. One is it is having amplitude or strength. Okay, amplitude or strength, and it is having a direction. Okay, it is having a direction. So the quantity which is having a direction, it is a measure or it is a quantity which is having a direction and amplitude, strength, that is termed as vector. Here also, vector is formed. Now this vector, because of the dipole, there will be flow of current. Okay, there will be flow of current, vector is produced, small factors. Now, if we sum all this, we have seen small, these are the vector, dipole, they are creating vectors. These vectors are creating, directing, actually the vectors are, it is represented as an arrow. It is represented, the vector is represented by a arrow. This arrowhead signifies in which direction current is flowing. In which direction current is flowing. And this is the strength, magnitude or amplitude of this quantity. Okay, now we will see this. Here it is very small vectors. Small vectors. These are very small vectors. Some is moving towards this, some is moving towards this, some is moving towards this, some is moving towards this. See, small vectors are having different directions. But most of the directions, if I sum all these small vectors, we will get a mean vector. We will get a mean vector. And suppose this is the mean vector. So this mean vector is larger than the other small vectors. And this arrow indicates in which direction current is flowing in the heart. It is always from the base of the heart toward the apex of the heart through the interventricular septum. Okay, so we'll find this is called mean vector. So you understood what is vector and what is mean vector. And this mean vector is called electrical axis. This is also called since we calculate this vector using the QRS wave of the ECG, it is also called QRS axis. Okay, so various names can be given to it. One is cardiac vector, or cardiac axis, or electrical axis or electrical vector or QRS. Since we measure it using QRS wave of the ECG, so it is also called QRS axis. You can, in some ECG recording, you will find T axis. You can find P axis. Means these are determined for using the P wave, no, instead of QRS wave. So if you use the P wave for determination of axis, then you can get the P axis. You can, in this way, you can get the T axis. But more commonly, usefully, we use QRS axis. Now let us define what is cardiac axis. What is electrical axis? Okay? Okay. Mean cardiac axis. It is the direction of flow of current. It is the direction of the flow of current, direction of the flow of cardiac impulse. Where it is generated? In the SA node. This current is generated in SA. So, flow of cardiac impulse, flow of current, flow of depolarization wave, same thing. Or the flow of EMF, electromotive force, flow towards the direction from the base of the heart towards the apex of the heart. Okay, so vector it indicates the direction of the flow of current in the heart. Generated this flow of current, it is generated where? In the heart. And this flow of current, at a flow of current or depolarization at a particular instant. This is not permanent. Every time it is changing, wave swan. It is every time this wave is every time activation front is every time it is moving. So every time the mean axis is changing. So this mean direction, mean average direction of movement of current generated in the heart. What is the direction and what is the intensity? So direction and intensity at a particular direction, and what is the direction of what? Flow of current, flow of depolarization, flow of or movement of activation front. Okay, so this is the mean axis, and this should be recorded at a particular instant, any moment. Suppose now axis is one just immediately after that this axis will be changing. Again after a few seconds it will be changing. So it is changing. At a particular moment, what is the axis that can be recorded? Okay, so this is the definition of cardiac axis. You will get it in this PPT. So these are the activation, this is the dipole and this is the activation front. And now this area, these cells are depolarized. Now at the next moment these will be depolarized. In the next moment this will be in this way activation front will proceed. And when all these dipoles are summated, then we will get a mean axis. This mean axis we are going to record. We are going to calculate. And these are going to give you various informations. Since it is every time it is changing, the impulse cardiac impulse generating in SA node, and it has got a path, conductivity. It has got some conductive tissue. Through these tissues, this will pass. If there is any abnormality in the conductive path, this is going to be changed. This mean axis is going to be changed. Okay. Similarly, if there is any change in the mass of tissue, this is the ventricular wall. So if it is wall is increased, mass is increased, again what will happen? This mean axis will be changed. If the mass of the wall of this right ventricle is increased, then this mean axis will be directed towards this. If this is mass is increased here, this mean axis will be directed towards this. So by studying this mean axis, we can also assess whether there is hypertrophy of the heart. In the left ventricular hypertrophy, as well as the hypertrophy can also be there in right ventricle. So by measuring the axis, mean axis, we can say whether there is right ventricular hypertrophy or there is right ventricular hypertrophy. Moreover, this is going to be changed if there is any change in the conductive pathway. Suppose there is a blockage in right bundle branch or in the left bundle branch blockage or in the anterior fascicle. There are two fascicles of the leg bundle, anterior fascicle and posterior fascicle. If one of the fascicle, I will discuss it in my next class. One fascicle, it is blocked. Then we call it fascicular block, monofascicular block, only fascicular block. Okay, or hemi block. Simply we call it hemi block. When both the fascicles are blocked, then it is bifascicular block. When these both fascicles of the left bundle branch as well as the right bundle branch, all three are blocked, then we call it trifascicular block. When the AB node is blocked, then we call it AB block. Now it is completely dissociated from SA node. So, complete heart block. We will discuss it in my next class. There are different types of heart blocks, first degree, second degree, third degree heart blocks, and we will do different types of arrhythmias. We will also discuss, we will also elaborate different, which is very important, this coronary myocardial infarction, coronary ischemia. Okay. Now, one more thing that you have to remember. When the direction, it is the lead 3. When the direction of current is towards this, towards lead 2, it will create a positive wave. When the direction is, here it will be a positive wave, here it will create negative wave. When the direction of flow is away from the positive lead, then it will create negative wave. When the direction of this flow is towards the positive lead, it will give a positive wave. You have to remember this thing. This direction of the flow, if it is towards a positive pole of the electrode, it will create positive wave. If it is away from because we will find same in one lead it is giving positive wave, in some other lead it is giving negative wave. It is because of this only. The anterior fascicle, posterior fascicle, they can be blocked. Here it can be blocked. This can be blocked. What is written at the top? The cardiac axis refers to the overall direction of the electrical activity of the heart during ventricular respiration at a particular instant. Now, what is, because this will be required, we using Einthoven triangle and Einthoven principle, we will determine electrical axis of the heart. Einthoven triangle, what is Einthoven triangle? It says it is a triangle, assume a triangle. Triangle, isolateral triangle. Assume a isolateral triangle on the chest, keeping the heart at the center. They assume it. So at the isolateral triangle, at the center there is the heart. Okay, and how can I draw this triangle? Connecting both arms, lead 1, connecting left arm and left leg, okay, lead 2, and connecting left leg to left arm, it is lead 3. So this is a triangle. So at the center of the triangle, what is the heart? Okay, now this Einthoven's law, it states, what it states? The sum total voltage of this lead, and this lead is 0. If you get the sum of lead 1, lead 2 and lead 3, what will be the result? What will be the voltage? 0. Okay. It also states the voltage of lead 1, voltage difference of lead 1 and the voltage difference of lead 3. If you sum both, you will get, it will be equal to the voltage of the lead 2. Means voltage of lead 1 plus voltage of lead 2 and plus voltage of lead 3 equals to 0. It also says, if you get voltage of sum total voltage of 1 and sum total voltage of 3, it will be equal to that of lead 2. This is Einthoven's principle. Regarding, he developed this principle regarding a volume conductor. In a volume conductor, where current can be flow, within this conductor, if you think of a triangle, there will be 3 points. So, difference between 2 points, this and this point, difference between this and point, difference to this point, if you sum it, it is 0. That is applied here by Einthoven in case of heart. Okay, so you try to know this. So cardiac axis vector, what is there? We see this vector will be having two things will be there. One will be the direction. When we will be determining the electrical axis, you have to say the direction. How can you say the direction? You are looking at the heart in the frontal plane. So this is one direction of the heart. This is another direction. This is another direction. Okay. In this, heart may be at different direction. So similarly, the electrical axis may be at different direction. Means some degree you have to mention. What is the degree? What is the degree? You just think of it is 180 degree, 360 degree. Okay. Now at what degree our heart lies? Okay. That is the mean cardiac vector. And this vector is having a strength and this is the voltage. And you can get this value, from where? From the voltage of different leads. From the different leads, you can determine this intensity of this, what is the intensity of this, what is the strength of this, and what is the direction of this vector. Okay. Well, let's see now. We will explain how it is determined. So you know this? Okay. Actually, we use electrode here and here. But for drawing Einthoven triangle, what we do? We shift this point to here. The same only. Because they are electrically they are connected. And loss of current loss of voltage will be very, very minimum. So we can shift this point to here. Similarly, we can shift that point to here at the root of the limb. And we can also shift this to the root of this limb to here. As a result, what we can get? This. Okay, now we can get this. So this is the Einthoven triangle. At the center, it is the heart. Okay, always you have to remember, see the lead 1, that side is positive, this is negative. And for lead 2, this is negative, this is positive. For lead 3, that one is negative, it was positive. It has to be remembered always. Now, what are the factors that affect electrical axis? 4 factors. What are these 4 factors? Number 1 is electrical activity of the heart. If it is normal, okay, it will be at a particular direction, and we know the direction from the base to the apex of the heart through intervertebral septum. And conduction of the cardiac impulse. If there is any problem in the conductive pathway, for example, right bundle branch or right bundle, we will see that if there is shifting of the cardiac axis. Ventricular wall thickness. If thickness, where the thickness is here, the shift will be moved to this side. If the thickness is right ventricle, the shift will be towards the right. Okay, so ventricular wall thickness also an important determinant of cardiac axis, and anatomical location and position or the orientation of the heart. Sometimes heart is like vertically, it may remain obliquely, it may remain horizontally. Okay, it happens during right axis deviation, it happens during left axis deviation, and it is the normal axis. Okay, so what is the orientation of the heart? What is the position of the heart? We can also assess from electrical axis or cardiac axis. So, determination of cardiac axis, how can we determine? First, I will describe one easy method. For this easy method, what you have to do? Only you have to look at 2 leads. One is lead 1, another is AVL. Write it down. One is V1, another is AVL. Okay? So, in V1, suppose this is P wave, Q wave, R wave, S wave, and T wave. It is in lead 1. This is the QRS complex. This is the QRS complex. Now, this is the isoelectric line. The wave that is below the isoelectric line, this is the negative wave. So, S is the negative wave and it is the positive wave. What is the algebraic sum of? What is the algebraic sum of QRS wave? Means R wave minus S wave. That is negative. So what is the net wave? Net deflection positive. Okay. So here it is positive or net deflection positive or negative? It is positive, mostly positive. Suppose this is 7 mm and this one is 2 mm. So what would be the net? So it is minus. So 7 plus 7 mm, it is plus 7 and it is minus. So minus 2 mm. Net voltage plus 5 mm. So in lead 1, it is positive. So in this way, if it is positive, if this QRS complex is positive also in ABL, then we will say the axis is normal. Okay? So if QRS axis, net QRS axis, both are positive, then axis is normal. Okay? upper half of this circle is negative and lower half of this circle is positive. Okay. 0 degree, 180 degree. This is 90 degree plus. This is 90 degree minus. Okay. Minus 30, minus 60, minus 120, minus 150, and here similarly plus 30, plus 60, plus 90, plus 120, plus 150. If the axis lies between these and these, this is the normal range. From here to here, this is the normal electrical axis. From 110 plus 110 to minus. If we determine your electrical axis and if it lies within this range, then your axis is normal. If the axis lies beyond this, then it is called left axis deviation. Sorry, right axis deviation. This is, and it is left axis deviation, and when it exceeds 110, then it will be called as right axis deviation. Okay, we'll see what are the condition where this. So, by looking, now we are determining the axis. Now we can say whether it is normal or there is LAD or there is RAD. If QRS is mainly positive in B1, in L1 and also in ABF, the axis is normal. Okay, so first condition what? L1 ABL. Okay, QRS. If it is positive here, axis is normal. If L1 it is positive, but here it is negative, mainly negative, then there is LAD, late axis deviation. Simply, looking into this, you can determine whether LAD is there or RAD is there. And if it is negative in L1, the voltage is mainly negative, and in ABL it is positive, then it is RAD. Right? I will give one example. You have to determine and tell whether what type of deviation it is. I will give actual figure. Then, if both are negative, extreme axis deviation, that will be regarded as extreme axis deviation. That will be located here. In the circle, it will be located here. This will show extreme deviation. So this is about the rapid method. Okay. Now I am giving you the one of the accurate method involving Einthoven's method. So what you have to do? You have to draw a equilateral triangle first. So I am drawing a equilateral triangle. Can you give me a copy? Having hard. Yes, give it to me. Okay. Now you join. So I got the equilateral triangle. Then you have to find the midpoint of this triangle. How can you do it? First find the center of this. Suppose this is the center, 0. This is the center, 0. This is the center, 0. From the center, you draw perpendicular line. Okay? So I am drawing perpendicular line. So I got the center. This is the center. Now you draw a circle from the center, connecting all the corners. Next, इस सर्कल को हाफ करो, upper half, lower half, and this will go through this line. And this line should be parallel to this. Okay. Just see the procedure, what I am doing. That is the procedure. So this is 0 degree and this is 180 degree. And definitely this will be 90 degree and this will be 90 degree. And as I said, upper portion is negative, lower portion is positive. So it is minus 90 degree. It is from this way, it is minus 180 degree. If I look into this way, it is plus 180 degree. Okay. Now, this is L1, lead 1. Sorry, this is lead 1. This is lead 2 and this is lead 3. Isn't it? This is the Einthoven triangle. So this is lead 1, this is lead 2 and this is lead 3. And we know this side is positive and this side is negative. Positive, negative. And while this, what is this? This is negative and this is positive. Important. Otherwise we will calculate QRS in a wrong way. And for lead 3, it is positive, this side is negative. Okay? So now you are ready. You have to choose two standard leads. 1, 2, 3. The ABF, 1 and ABF. In one positive, positive, normal axis. In one positive, lead 1, negative, LAD. Negative, positive, RAD. Both are negative, extreme axis. Normal. See, in both way, one ABF positive, mainly positive. And in case of here, lead 1 positive but ABF negative, so it is left axis. Here lead 1 positive negative but ABF positive, so it is right. It is what? A right axis deviation. Choose any two. So this is 1 and this is 3. Calculate what is the net voltage of lead 1. Well, how much is the positive wave, R wave? 5, top में 5 and नीचे 4, 9. From here to here, how much it is? 9 millimeter. Positive R wave is 9 millimeter and negative wave 1 mm. So 9 minus 1, 8 mm. Okay, in lead, it is in lead 1. Where is my lead 1? So from here, you mark a point which is 9 millimeter. So maybe 1, 2, 3, 4, 5 from the scale, you measure. And this is positive side. The question is in which side it will make the point. Since the wave is positive, so I will make the point at the positive side. This is the negative side. So my point is here. My positive. Next, come to lead 3. It is negative. It is negative, isn't it? Positive wave, there is no positive wave. So how much is this? Here there is how many squares are there? 4. And here there is 2. Okay, 4 plus 2, 6. So these are minus 6. Minus is the negative wave, no? Minus 6. It is in lead 3. So come to lead 3. Where to put? This side or that side? This side. See, this is a negative side. My wave is negative. So draw a point which is from 0. Here is suppose this is the point. 6. Okay, so I got 2 points. One is here, another is here. Now I will draw 2 perpendicular lines from that 2 points so that they cross each other. Okay, fine. This is the perpendicular line. Another perpendicular line I will draw from here so that I will not draw this side. Why? Because no line is there. So I will draw to do this side perpendicular line. Okay. Now they will be crossing this side. I got the vector. How? Now join this with this. So put a arrow. So this is the direction of my electrical axis and it is the voltage. What is the distance? 2 millimeter. Say it is 9 millimeter. 9 millimeter means 1 millimeter is 1 millivolt, 0.1 millivolt. 1 millimeter means 1.1 millivolt. Since it is 9 millimeter, so I got the vector. So what is the strength? 9.9 millivolt. And what is the direction? It is just 0 degree and here same it is minus 5 degree. So your electrical axis is minus. Can you understood this? So first what you do, I have to draw a triangle. Then Marking is important, which side? Positive, negative, it is important. Then here's the center. Then draw a circle. Make it half, upper half, lower half. Then every side, okay? If anybody is having any doubt? No, okay. So this is the accurate method. Accurately, you can determine. There is another example. Right axis deviation is seen in this case. You write this. I don't have any time left, no time left. So right axis deviation is seen in this condition. In addition to right ventricular hypertrophy, LVS says left axis deviation is seen in this condition, and extreme right axis deviation is seen in this. So these points are very important. So these are the three methods. One is rapid method, another is accurate method. It is triaxial using Einthoven's law. Another is hexaxial reference. This is also a rapid method.